covering derivative rules. I started last time section 1.5, and I'm going to continue with that and also cover section 1.6 today. And let me just go over the rules that we discussed last time. So there are actually two constant rules. And the first one just says the derivative of a constant is 0. Okay, and if we're talking about a function y equals f of x, I'm going to go over some notation. If you take the derivative of your function, remember, since y and f are the same and y equals f of x describes the function, the relationship between x and y, what we do is we use, if we're taking the derivative, dy dx. So d over dx is a notation for taking the derivative. That's what it means. We're taking the derivative of y. And this is called Leibniz notation, dy dx. And also another notation that I was using last time is f prime of x. That looks like an apostrophe, but we say prime, f prime of x is a way of denoting the derivative. Okay, so that's the notation that I'm going to be using. And sometimes I'll write f prime of x, sometimes I'll write dy dx. Another way of writing it is d dx of the function f of x. That's another way of denoting it. Okay. So for the second constant rule, if you have a function that can be represented as a constant multiple, so let's suppose we have y equals some constant times our function f of x. If I want to take the derivative of this, dy dx, that is the same as taking your constant and multiplying it by the derivative. So this constant multiplication is not going to affect anything. You just take the derivative of your function and multiply it by the constant after the fact, okay? And so that's the constant multiple rule. It's pretty straightforward. I think when we start to do some examples, these rules will make more sense to you. Another rule that we talked about last time was the power rule. And so if you have a function that is a power on x, then the derivative, you take the power, multiply it out front, and subtract 1 from your power. Okay, that's the power rule. And these two combined will, are often, you'll see this with polynomials. You combine these two rules, and I'll do some examples very shortly for that. So that was our third rule. Our fourth rule then, and our fifth rule are the sum and difference rules. Okay, the sum and difference rules are simply the derivative of the sum is the sum of the derivatives. And if you want to see that in math language, so if you have a function y equals f of x plus g of x, I have two functions added together, And if I want to take the derivative of dy dx, basically that's taking the derivative of the sum, and that's just going to be the sum of the derivative. So you're just going to take the derivative of f and add it to the derivative of g. That's the sum rule. And similarly, the difference rule is pretty much the same thing. I can put difference here in my language or my written rule here. So the derivative of the difference is the difference of the derivatives. And if I want to write that out, if y equals f of x minus g of x, then dy dx is the derivative of f of x minus g of x, that's the derivative of the difference, is the difference of the derivatives. Okay. So those are the sum and difference rules. And these are the rules that I introduced last time. Here's the power rule. And the constant multiple rule, and then the derivative of the constant being 0. So those 5 rules are the ones I introduced. I'd like to introduce 2 more today, and I'll just go ahead and give you those now, and then we'll look at examples to see how all of these different rules are applied. So the product rule. So if you have 2 functions that, or you have a function y that is a product of 2 functions, then the derivative dy dx, okay, you take the first function, f of x, multiply it by the derivative of the second function, and then add to that the second function multiplied by the derivative of the first function. Okay, that is the product rule. And then finally, the quotient rule is the last rule we're going to talk about today. A quotient, we have 2 functions. One is in the numerator and the other is in the denominator. And if you want to find the derivative of that quotient, then you take the bottom, which is g of x, times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Okay, that's the quotient rule. So if you want a copy, a prettier copy of these rules than what I'm scribbling out right here, and you just want to print something out, you can just Google these, and I'll come back to this. So if you haven't copied all this, let me just show you very quickly, and I'll come back to. So you go to Google and you just type in basic derivative rules. And there are many derivative rules, but for our purposes, we just want the basic ones. Here it just gives you right off the bat, here you have the derivative of the sum is the sum of the derivatives, and then you've got the difference rule. And if you click on images, you can see various different charts. There's one in particular that I like, this one right here. You can print that out. You've got the constant rule, the constant multiple rule, the power rule, the sum rule, the difference rule, the product rule, the quotient rule. And in 1.7, I think we're going to talk about the chain rule. That's next. But these are the main rules that you want to know. So this is a nice nice chart here that you can print out and put in your notes as a reference. Going back to the DocCam. I'll let you finish copying those rules there for your notes. Give you a moment to do that. By the way, because I have, my Mondays through Thursdays are pretty busy, and I don't get around to uploading the recordings for the lectures until probably about Friday. If you want to look at them sooner than that, because the reason why I upload them to YouTube is simply because they get deleted after a while. But immediately after, not immediately, but shortly after the lecture, maybe within a few hours, you'll see a link there. If you go into the Zoom online classrooms, you'll see a link for the recordings. And it needs a password, but somewhere in Folio, it gives you the password. And maybe that's in the email that I sent out with the link to the recordings. I haven't gone in there myself to figure out how to do that, but that is an option for you to investigate if you want to get a hold of the recordings sooner than, let's say, when I post them on Friday of the week, okay, at the end of the week. So just in case you didn't know that option is available. Okay, any questions on these rules? We'll cover the last rule, the chain rule, next week. So moving on, let's do some examples. This is how you're really going to learn this stuff, is doing lots of practice problems. So let's just get to it. And I will be referring to these rules as we do these examples. And I'll start out with kind of the basic ones, and just you can see the quotient rule is kind of a complex formula that you're going to use. So it will get more complex as we go on. But with our first example, let's suppose we have a function f of x equals 3x to the 5th power. Your hint there, because we have a power on x, is to use the power rule. But we also have a constant out front, so we're going to use a kind of a combination of the constant multiple rule and the power rule. And to take the derivative of this function, we take our power, 5, multiplied by our constant. That's going to be 15. And then you subtract 1 from your power. So this 15x to the 4th is your derivative. Stop me if you have any questions about anything that I do at any point. We don't have a square root rule, right? So you need to think of the square root as a power. And so you want to rewrite this function, f of x equals the square root of x. You want to write that as x to the 1/2 power. Now that we have a power, we can go ahead and apply the power rule. And I can't remember if it was this class, but at some point I said that the power was an integer. It doesn't have to be an integer. So obviously this is 1/2. I misspoke. So I don't know why I said that, but when we take the derivative, I can't remember if it was this class or another class when I said that, but if we take the derivative, we're going to take our power, multiply it out front, and then subtract 1 from that power. And when we subtract 1, of course, we have to have a common denominator. You know that 1/2 minus 1 is negative 1/2, but I'm just going to write it out here for you. So this is going to be negative 1/2. And that negative just means that x to the 1/2 is going to be in the denominator. So to simplify this, I put the x to the 1/2 in the denominator. And x to the 1/2 is, of course, the square root of x. So there's my derivative. Now, in your homework, when you're doing these problems in MyLab Math, you really don't have to necessarily simplify. They're very lenient, as picky as they are about so many different things. They're very lenient with derivatives. When you're typing in the answer, you could pretty much type this in, and you're going to get the answer correct. So you do not have to simplify it. But I always like to simplify just to show you how it's done. But there's no real right answer. This is correct. This is correct. You know, however you put it in there, they're very lenient, just so you know. Okay.
Ms. Wiggins.
Did you have a question?
Yes. Could you explain the step right before the before you got the final answer?
This one right here?
Yes, ma'am.
Okay, so at this point, remember we subtract 1 from the power, and 1/2 minus 1 is -1/2. That negative means that you take the reciprocal of your power on x. So we have x to the 1/2, but since we have -1/2, that negative means we take the reciprocal, which is 1 divided by x to the 1/2. So whenever you have a negative exponent, you take the reciprocal. Does that answer your question?
Yes, ma'am. Thank you.
Okay, thank you for asking. Okay. So let's do another one. Now this is the format that we want to write our function in. Typically we don't like negative exponents, so we like to put things in the denominator if they have a negative exponent. So this is the correct form, but when you're, for purposes of finding the derivative, you want to change the form to be f of x equals, now 1 divided by 3, that's the 1/3 is the constant out front there. And because x to the 4th is in the denominator, this is going to be written as x to the -4. Now that it's in the form of x to some exponent, I can apply the power rule. So when I take the derivative, -4 times 1/3 is -4/3. And I'm just going to write that as an intermediary step. Let's put -4 minus 1. That's better. That just shows you what I'm doing here. So we take -4 times 1/3 right there. So I get -4/3. And then you subtract 1 from the exponent -4 to get -5. Okay, this function is a polynomial, and we're going to use in this one, because we have constants that are multiplied in front of our powers of x, we're going to use the constant multiple rule. Because we have powers on x, we're going to use the power rule. We have sum and differences of these functions, these power functions. So we're going to use the sum and difference rule. And we're also going to use the constant rule, which says that the derivative of a constant is 0. So this example applies a lot of different rules here for the derivative. So when we take the derivative, just starting with the first term, and we're allowed to do each term separately because of that sum and difference rule. So 5 times 7 is 35, and then we subtract 1 from the power to give us 4. 3 times -2, that's -6. Subtracting 1 from 3 gives us 2. This, remember last time I did an example where I showed that the derivative of a linear function is its slope. So this piece of the polynomial is the linear part. So the slope of the line y equals 3x minus 10 is 3. So the derivative is 3. And it also follows directly from the power rule, because if you think of it, 3x has a power of 1. So if you take 1 times 3, you're going to get 3x to the 1 minus 1, which is 3x to the 0, which is 3. So that's how I got the 3 there. But instead of thinking of this automatically, you're just going to recognize this. Oh, this is a linear function here. I can just put the slope down, and that's my answer. Okay, that's to me a little bit more direct of reasoning than going through this process. So there's my derivative. There's my derivative from the previous problem. Okay, any questions on that? Yes?
We can just leave out the -10?
Well, the derivative of a constant is 0, so you're right, yes. You're just gonna, you don't have to write the 0 down, yeah. So whenever you see a constant in your function, if you're taking the derivative, as long as the constant is by itself, it's just gonna go away when you take the derivative. Thank you. Any other questions? All right. Let me do another one here. So again, there's no rule for radicals. But if we think of this radical as an exponent, so I want to convert this to x. Remember, the power on x is the numerator and the root is the denominator. So this is x to the 7/6. Now that it's written as a power, I can apply the power rule. So when I take the derivative, I have 7/6 x. I'm going to subtract 1. When you subtract 1, think of this as 6/6, right? And so we have 7/6 x to the 1/6. And I would prefer to write it as the 6th root of x, like that. Now, sometimes when you're asked to calculate a derivative, you're going to be asked one step further to actually find the slope of a tangent line at a certain point. And that's when, so in other words, you want to find the derivative evaluated for a certain value of x. So you'll see that in your homework. So let me do an example like that. You're given a function (3x³ minus x² plus 7x minus 1). And you want to find f prime of 2. So first you're going to find the derivative, which is f prime of x. And you're going to, this is a polynomial, so you just start with your first term, applying the power rule. 3 times 3 is 9x. I'm going to subtract 1 from 3, so my power on x is going to be 2, 9x squared. Now moving on to the next term, take your power. This is understood to be -1. 2 times -1 is -2. Subtracting 1 from 2 gives me x to the first power. Well, that's just x. And then here we have our linear function, 7x minus 1. This has slope 7. So there is your final constant term coming from this linear function. But we're not done yet. Remember, they're asking for f prime of 2. So in order to do that, we just plug 2 in for x. Everywhere I see an x, I'm going to plug in 2. And then I'm going to calculate this value. 2 squared is 4 times 9 is 36. Minus 2 times 2, that's minus 4, plus 7. And if you do that calculation, 36 minus 4 is 32, plus 7, that's 39. So just as a reminder, what does this number mean in the context of this problem? This just says that 39 is the slope of the tangent line for your function at the value when x equals 2. That's the interpretation of that number. 39 is for the slope of a line. That's pretty steep. Maybe we can take a look at that on Desmos so you can see what that looks like. Polynomials are continuous smooth curves, and let's just take a look at that. So I'm going to go to Desmos. Desmos is very useful. It's a graphing calculator. I like using a graphing utility online as opposed to on a graphing calculator. It's just, you know, easier to look at because the screen's much larger. So my original function, my f of x, if you will recall, is y, which is f of x, equals 3x. And if you use this down here, you can type in exponents. 3x cubed minus x squared plus 7x minus 1. Okay, now the point of interest is x equals 2. So we're right here, this is x equal 2, and I need to drag the graph down to see where my function is at x equal 2. So it looks like right here, And if I want to calculate the tangent line, the slope is 39, and you can see right at this point here, the slope is pretty steep. So if I were to draw the tangent line here, I'm not sure what the intercept would be. I'd have to go ahead and find that. But if I plug in 2 into my function at that point, well, I'd have to go ahead and solve this problem. That was not what I planned on doing. I'm going to do another one later, but you can see that slope of the curve is pretty steep there. So that makes sense that the tangent line that passes through here is going to have a slope of 39. Okay. Let's see. Let's go back to our notes. All right, so we've covered pretty well the first 5 rules of derivatives. And I've done quite a few examples here using those rules. Now let's move on to what we call the product rule, okay? So I'm going to do a few examples, or at least using the product rule and the quotient rule. And let me just remind you what the product rule is. If we have a product of 2 functions, f of x and g of x, then the derivative of that product is going to be the first times the derivative of the second plus the second times the derivative of the first. Okay. First function times the derivative of the second plus the second function times the derivative of the first. So for our particular example, we have 2 linear functions multiplied. So this one is 2x minus 3 times 3x plus 4. So the first function would be this one right here, which is multiplied by the second one. So the first function is 2x minus 3, and this is a linear function, and the derivative of that is simply 2. The second function is the 3x plus 4, and the derivative of that is simply 3. So I have all the information here that I need for my formula. Now it's just a matter of plugging in these functions. So the derivative dy dx is f of x times the derivative of g, which is 3, plus g of x, which is 3x plus 4, times the derivative of f, which is 2. And now to simplify this, I need to distribute these constants using the distributive law. So this is going to be 3 times 2x is 6x. 3 times negative 3 is negative 9. 2 times 3x is 6x. And 2 times 4 is 8. So now I'm going to combine like terms. 6x plus 6x is 12x. Negative 9 plus 8 is negative 1. So this is my derivative. Now, in your homework, when you get into problems like this, it'll ask you to do it 2 different ways. So there's a lot of times with these derivatives, you can do it more than one way. So just to verify that this is in fact the derivative, Let's do it by, let's calculate the derivative. Instead of using the product rule, let's just multiply this first and then apply the power rule and the sum and difference rules. So, so our original function, of course, is 2x minus 3 times 3x plus 4. If I multiply these first, I'm going to FOIL. The first would be 2x and 3x. Multiplying those together, I get 6x squared. The outside terms are 2x and 4. Multiplying those together, that gives me 8x. The inside terms are negative 3 and 3x, so that's going to be negative 9x when I multiply those two. And finally, the last terms are negative 3 and 4, so I have negative 12. At this point, I want to combine like terms, and I get 6x squared minus x, because 8x minus 9x is minus x minus 12. Now I take the derivative, and instead of using the product rule, because I've already done the product, right? Instead of using the product rule, I'm going to just use the power rule here. So 2 times 6 is 12x. And then this is the linear part. The derivative of the constant is 0. Here, the slope is negative 1. So taking the derivative of the linear function, negative x minus 12, I get negative 1. And as you can see, as it should, it matches our first answer, because we were taking the derivative of the same function. So obviously, we're going to get the same answer. But we just did it in 2 different methods. And it's a way of showing you that the product rule does work. And sometimes it's easier to use the product rule. Sometimes it's easier to multiply first. It just depends on what your functions are. Any questions on that? Okay, our next example uses the quotient rule. And just to recall, the quotient rule says that if you have a function that is expressed as the quotient of 2 functions, f of x and g of x, then to calculate the derivative, we take the bottom function multiplied by the derivative of the top, then we subtract the top function multiplied by the derivative of the bottom, and then all of this is divided by the bottom function squared. Okay, that is the quotient rule. So let's say that we have a function y equals 2x minus 3 over 3x plus 4. So in the previous problem, we were taking the product of these 2 linear functions. Now we're taking the quotient. So it's a whole new function, and because it's a quotient, we have to use the quotient rule. So the derivative y prime, or if you will, dy dx, same thing, this is just another notation, is, well, let me go ahead and list the functions. We have the top function, which is 2x minus 3, and its derivative is 2. the bottom function is 3x plus 4, and its derivative is 3. So I'm going to take these functions, just like I did when I was using the product rule, except now I have a different formula. I'm just taking these functions and plugging them in according to the formula. So g of x is 3x plus 4. That is multiplied by f prime of x, which is 2. Then I subtract the top function, which is 2x minus 3. That's my f of x. And I multiply that by g prime of x, which is 3. Before I'm done, I have to take the entire numerator there and divide it by g of x squared. Okay? Oops, I was supposed to plug g of x in. Sorry, I meant to do that. G of x is 3x plus 4. Okay? And then we square that. So to do this, I'm going to distribute the 2 and the 3. And I also have to distribute this negative, right? So 2 times 3x plus 4 is 6x plus 8. A negative 3, because I have 3 times this negative here, that's negative 3 times 2x minus 3 is negative 6x. The double negative is going to give me plus 9. And then when I FOIL 3x plus 4, okay, let me do that over here. 3x plus 4 times 3x plus 4. The first give me 9x squared. The inside and outside is 12x because we have 3x times 4. Inside is also 12x, 3x times 4. So plus 24x. And finally, 4 times 4 is 16. So this is going to be the denominator. And then we're going to cancel 6x minus 6x is 0. 8 plus 9 is 17. And there you have the final answer for your derivative. So the quotient rule is a little bit more involved than the other rules, but it's certainly doable, nothing too hard. All right. So now that I've introduced all the rules to you so far, we just have the chain rule left. But let me do some examples of the type of problems you're going to run into on your homework. That may be a little confusing for you, so I just want to show you how to deal with those. The first example that I'd like to do is find an equation for a tangent line given a function and a point where it passes through. So if there are no questions on the quotient rule here, I will go ahead and move on to example 10. All right, the question reads, find an equation for the tangent line to the graph of y equals negative 2x divided by x plus 1 at the origin. So whenever you have to find an equation for the tangent line, remember the derivative gives you the slope of all the tangent lines at all the points. And the derivative is a function of x. So depending on which x value you're looking at, you're going to have a different slope. And so it's a function of x. But in this particular problem, we are specifying that we want a particular tangent line. That's why we're looking for the equation, one equation for a tangent line for this function, and then they have to give you a point. And this one says at the origin. And of course, the origin is the point 0, 0. When you're looking for the equation of a line, you need a slope and an intercept. Most of the time when you run into this problem, they don't give you the intercept, they give you a different point. But this particular point is actually on the y-axis. The origin is 0, 0, lies on the y-axis. So this is the intercept. So we don't have to hunt for a b. We can see right off the bat that b is that value. And that's because this is a 0. The intercept always has x value 0 and then some b value. In this case, it's b equal to 0. So when I've done these examples in the past, we had to hunt. First we found m and then we had to find b. Here we already know what b is. So all we have to do is find the slope. And of course we use that, we find the slope by calculating the derivative and plugging in x equals 0. So let me show you how we do that. When we calculate the derivative of this function, you can see we have a quotient here, right? The top function is negative 2x and the bottom function is x plus 1. So I'm going to use the quotient rule to find the derivative. And the quotient rule, remember, you take the bottom function, which in this case is x plus 1, times the derivative of the top. This is linear, so the derivative is negative 2, minus the top function, which is negative 2x, times the derivative of the bottom. Well, the bottom is x plus 1, which is a line, so the derivative is the slope, and the slope is 1. So here we have, let's review this. The bottom function times the derivative of the top minus the top function times the derivative of the bottom. All of this is going to be divided by the bottom function squared. Okay? So this is the quotient rule. I'm just going to put this in parentheses to remind you of the rule. Okay. Now I'm going to simplify this. So we have negative 2x times x plus 1 is negative 2x minus 2. And then we have 1 times negative 2x, but we're subtracting that. So it's going to be a double negative. So it's going to be plus 2x. And you'll notice there that my negative 2x cancels with my 2x. And this becomes negative 2 over x plus 1 squared. All right, now this is the derivative, right? We are looking for the slope of the tangent at the origin. So we need to plug in x equals 0 into our derivative. So m is -2. And that means that our b value, which is 0, and our m, which is -2, gives us the equation for the tangent line. And that is y equals -2x. Okay, so we found the equation of the tangent line. Let me just take you over to desmos.com to show you what this looks like. All right, so we're going to look at the graph of this function and then the graph of the tangent line. So our original function is y equals -2x divided by x plus 1. And let's just look at that. Remember, we're looking at the tangent at the origin. So let me go ahead and mark the origin. That origin is the point 0, 0, and there it is colored in blue. And now I'm going to put the tangent line there, which we found to be y equals -2x. There it is. Okay, so that, here's the red is the original function, here's the origin, and this is the tangent line that goes through the origin, and it's tangent to this red function. Okay? So that's kind of a visual understanding of what's going on here. Sometimes when you're just looking at equations, it's hard to really know, you're just kind of manipulating equations around. It's hard to really understand what you're doing. So I always like to have a picture. So I encourage you to use Desmos to help you understand this stuff and bring it all together. Are there any questions on this one? Before I move on? All right, another type of problem that you're going to run into in your homework that might be confusing. It's actually really an easy problem to do, but the wording of it is kind of strange and maybe not what you're used to. So let me just walk you through it to avoid that confusion. I can't remember which homework problem it is, but it's in there somewhere. Okay, we're given a function y equals x squared plus 6, let's say. And the question is, where is the tangent line having, where do you find the, okay, find where you have a horizontal tangent. Okay, so there's some key words here, all right? First off, it's saying where. In mathematics, whenever you're asked where, usually, almost all the time, it means you're looking for an x value, especially if you're talking about a function, okay? So this is your clue that looking for an x value. The second hint is, first off, when it says horizontal tangent, this is telling you you're looking for a horizontal line. And what is the key thing about a horizontal line? M is equal to 0. Okay. So it's asking me where, so I'm looking for an x value, but I'm also noting that m equals 0. So the derivative, remember, for your function is the slope of the tangent. And to take the derivative of this y equals x squared, we apply the power rule. The derivative of the 6 is 0, but this is 2 times x, and then you subtract 1 from 2. So that's going to give you a power of 1, which is just plain old 2x is your derivative. And because we're saying, so this is the slope of the tangent, for, and we want this to be 0. So you just set it equal to 0, right? Well, remember, we're looking for an x value, and we know that 2x equals 0, so what is x? Well, it just means that x has to equal 0. So this is where we have a horizontal tangent, and typically the answer, they might ask for x equals 0, but they typically want a point. So once you find x, you just plug in 0 to find y. And so when we do that, we get y is equal to 0 squared plus 6. So our point x is 0, y is 6. So we have 0, 6. That's where our tangent, okay? So let's just verify that again in Desmos. Here's our original function, y equals x squared plus 6. And we're looking for a horizontal tangent at 0, 6. That is going to be the line for y equals 6. Because remember, the function, if you have a horizontal line, it's just a y value. And in our particular instant, y is 6. So going to Desmos, oh wait, there's some chat here. Let me check this out. What rule was that last problem? What rule was that last problem? This one was the power rule, and this one up here was the quotient rule. Okay. So going to Desmos. We have y equals x squared plus 6. Okay, so this is our function. And you can kind of see where the horizontal tangent is. There's x is 0 and y is 6. And the equation for our horizontal line is just simply y equals the constant, in this case 6. And so there's our horizontal tangent for that quadratic function. Okay. Any questions on this one? Another one asks you, where is the tangent line having slope of negative 18? And the function that we're given is y equals 4x squared minus 2x. So calculating dy dx, here's our function. We take 2 times 4, that's 8x. Subtract 1 from 2, we get 1. This is the linear part, so the derivative is just negative 2. And we want this to equal negative 18. So solving this equation, we are going to add 2 to both sides. And so we get 8x equals negative 16. Then we're going to divide by 8. And we get x equals negative 2. So this answers the question where, and if you want to calculate the y value for that point, so we have negative 2, and we want this y value there. We just plug this into our original function, and y equals 4 negative 2 squared minus 2 times negative 2. And if you calculate this, 4 times 4 is 16. This is a double negative, so that's going to be negative 2 times negative 2 is plus 4. 16 plus 4 is 20. So that's going to go right there. And so the where question is negative 220. That's the answer. So those are a couple homework. Another homework problem that you're going to run into, let's do an example like that, is you have a population of a city, and in T years it grows from 500,000 to a size given by a polynomial function 500,000 plus 1,000 t squared. So let me go ahead and write that. All right, so this is the function. You can see when t equals 0, that's at the start of the time period. The population is 500,000. So if this is 0, then we just have 500,000. Okay. The question that we want to answer is, what is the population after 10 years? Or that's one of the questions. It's supposed to say after. Okay. And that just means we're going to take 10 and plug it into our function for the population. And 1,000 times 100 is 100,000, so this is going to be 600,000. Now, another type of question that you might be asked is to find the rate of change at time t. And remember we talked about the average rate of change? Well, that was over an interval. We are talking now about at a specific time, which is a point in time. So we're not talking about a time interval. We are actually want to find the instantaneous rate of change at an instant in time. So that's the derivative. Remember when we calculated the derivative from the definition, we started with an interval of h, but then we reduced that down to, we let the limit as h approaches 0 in the definition of the derivative. So you're reducing that down to an instant. If your time interval goes down to 0, you're talking about an instant. Okay, so that's the derivative. That's your hint. If it just says plain old rate of change, think derivative. So I'm going to take the derivative of my function here. P prime of t is, well, the derivative of a constant is 0. And here we have we're going to use the power function. 2 times 1,000 is 2,000. And then times t, because you subtract 1 from the exponent, which is 2 minus 1 is just 1. And that's t to the 1 power is just plain old t. So there's our derivative. That's the rate of change at time t. So if we want to find the rate of change at t equals 10 years, then we just plug our 10 into our derivative function. And that is 20,000. So obviously the population starting out at t equals 0, it's increasing by, well, after 1 year, the rate that increases is 2,000. And the rate at which it increases is going up also. So by the time you get to year 10, you're increasing at a rate of 20,000 per year. So that's how that works. There's another problem very similar to this one that uses a function which is actually a quotient. So let me show you how to calculate the derivative for that. Any questions on this particular problem? Okay. So I'm just going to show you how to calculate the derivative. If you have a population that is modeled by this function and you want to find the rate of change, this is a quotient. So to find the rate of change, you have to use the quotient rule. So let me just show you how to do that. Remember, you take the bottom function times the derivative of the top minus the top function times the derivative of the bottom. 2 times 2 is 4t, and this, of course, is a constant. The derivative of that is 0. Then you take the entire numerator divided by the denominator squared. Okay, so that's how you would calculate the derivative for that. And like I said, they're very lenient. MyLab Math is very lenient on how you put the derivative in your answer. So if it's asking you to calculate a derivative, you can just leave your answer like this. You can just enter it in just like this. But if you want to simplify it, you would distribute your 600. So that would be 1200 t squared. And then if you want to do 25 times 600, that's 1500. So that's going to be plus 1500. Then you're going to subtract 6 times 4 is 24. So that's 2400 t squared, all divided by, if you square this out, you would get 4t to the 4th, and then plus 100, I'm just foiling here, t squared, and then plus 625. And simplify that. This is going to be negative 1200 t squared plus 15. By the way, let me think, did I do that right? Yeah, that's right. And so at any point, as you're simplifying this, MyLab Math will take any one of these answers. So honestly, if I were taking a test and I would be worried that I'd made a mistake here, I would just put this one in, because, you know, every time you try to simplify it, you're going to introduce the possibility of making a mistake. So why not just put it in like that, right? If they're going to let you do that, and they do, for derivatives. A lot of other problems, they're very picky about how your answer is, but when you're, I don't know, they have a lot of leniency when you're calculating a derivative. I don't know why that is. That's just how the software does it. But that's a little tip there for you. So I've covered everything that I want to cover today. Are there any questions? Your homework for section 1.4, 1.5, and 1.6 will be due not on Monday because it's a holiday, so on Tuesday at 11:59 p.m. And there's no quiz this week. The next quiz covers 5 sections, so I still have to cover 1.7 and 1.8 before you can take the quiz, and that will be next week. Okay. All right, well, if there are no questions, then I'll just sign off here. Have a good weekend.